Hello everyone, in this video we are just going to develop the UART peripheral drivers which is also required for the RTOS development process. Let's get started. So in the previous video we just developed the bare metal driver for driving an LED which is connected to PA5 of the same Nucleo development board, and in this video we are just going to develop UART serial communication TX process which will be most likely helpful for our RTOS development process, that is real-time operating system development process. So we are just going to do that in this particular video from scratch, and you can see this is the Nucleo development board, and in this development board by default there is an UART port connected to this ST-Link driver. So you don't want any external UART to USB converter for visualizing the output that is coming out of UART channel of the STM32f4 microcontroller in this development board, because we already have one in this board itself which will be connected to the PC through mini USB cable right over here. So the UART which is by default connected to the Nucleo ST-Link driver is USART2. So that USART2 is the one which we are going to configure, and we are going to initialize that TX function of that particular USART2 in this particular video with the help of bare metal programming. I am just going to open the STM32 Cube IDE, and in this Cube IDE you can see this is the previous program that we wrote, that is LED blink program. And now similar to this LED I am just going to create a new header file for USART. So USART.h, and similarly here I am just going to create a source file for USART, USART.c. Similar to the LED I am just going to add this header, and along the header I am just going to write definitions of three functions: UART TX init, and this receives a parameter of unsigned long, and the next function that I am going to write down is UART transfer, which receives a buffer. So I'm just giving a pointer right over here, and next function is UART write, which receives a byte of data. So this UART write will help us to transfer 1 byte of data over the UART bus, and this UART transfer will help us to pass sequential of bytes or characters through UART buses. For example, a word can be transmitted using the UART transfer function, and a single byte can be transferred using the UART write function. This will initialize the UART port of the microcontroller. I am just saving this. Let's try to write down the function definitions inside the USART.c file. Here I am just going to USART.h. I am just including the USART.h. Coming to the first and foremost thing that we want to do, we just want to find the clock of USART in the microcontroller, and we want to enable the clock of the USART bus. And the next thing that we want to do is set PA2 pin as alternate function mode in GPIO registers for configuring the PA2 as USART TX pin. And the next thing that we want to do is set the alternate function for PA2 as USART TX in that respective register. Next thing is you just want to enable the USART2 clock. Next is you just want to set the baud rate for the communication, and then the configuration of the transfer direction, And finally, we just want to enable the USART module. That's it. So for enabling the GPIO pins of the USART communication, we just want to find which USART we are just going to use. And as I mentioned, we are just going to configure and use the USART 2 module, since that is the USART which is connected to the already available ST link in my Nucleo development board. So we are just doing this because we don't want to add any external hardware like USB to UART converter for demonstrating the UART communication in our PC. So USART 2 is the one. So for USART 2, PA2 is the TX pin and PA3 is the RX pin. So that is well known. So we are just going to configure only PA2 as TX pin. We are just going to configure and use only the TX process of the USART function. We are not going to touch upon the receiver section. Just keep this in mind. And now for enabling the clock of the USART 2, we just want to find out to which bus the USART 2 is connected in our microcontroller. From the data sheet, you can clearly see GPIO-A is connected to AHP1 bus, and the USART 2 right over here is connected to APB1 bus. So just remember, GPIO-A is the one through which we are just going to perform the USART operation. So we just want to enable the GPIO-A bus first, and then we want to enable the USART bus for USART communication. So this is the thing that we are going to do first. So we are just going to move to ASP1 ENR register for enabling the GPIO-A bus, and then we are just going to move to the APB1 ENR function for enabling the clock of USART 2 module. And this time from the reference manual, we found out that GPIO-A bus can be enabled by setting the bit number 0 of ASP1 ENR function, and the USART 2 clock can be enabled by setting the bit number 17 of APB1 ENR register. So we are just going to do both of these. So RCC is the RCC pointer. This time AHP1 ENR, we are just going to set bit number 0. And here, coming to the USART 2 clock, we are just going to use the same RCC pointer, this time APB1 ENR, and we are just going to enable the 17th bit. And here I am just going to give a name for the variable, that is baud rate. Here I am just going to give it as data. Here also I am just going to give it as data. The next thing is we just want to set the PA2 mode as alternate function mode in GPIO registers. So for doing that, as usual, we are just going to the mode R register of the GPIO peripheral, and we are going to give this value for the corresponding PA2 bits. So these two bits correspond to PA0, these two bits corresponds to PA1, and these two bits 4 and 5 corresponds to PA2. So what we are going to do is we are just going to set this 5th bit and clear this 4th bit. That's it. GPIO-A mode R, set this 5th bit, and GPIO-A clear this 4th bit. And next thing is we just want to set the alternate function mode for PA2 as UART TX. So for setting the alternate function for a corresponding GPIO pin, this register is used, and in this register you can clearly see each pin is having 4 bits for configuration, and the first 4 bits corresponds to PA0, next 4 corresponds to PA1, and so on. And for PA2 we are just going to configure and use 8, 9, 10 and 11 bits of this same register. And similar to GPIO AFRL, we are also having H register, which is corresponding to next 8 pins of the microcontroller. So for now we are just going to set 8, 9, 10, 11 bits for configuring PA2. And now what will be the value that we want to configure right over here? So that is a big question. So for that, we just want to refer the datasheet of the microcontroller for checking which bits corresponds to USART 2. You can see in this alternate function table in page number 57 of datasheet of the microcontroller, if I want to select USART2 option TX in PA2 pin, I just want to configure the alternate function 7 in that particular register. That's it. So alternate function 7 is nothing but 0 1 1, which means I want to write 0 to 11th bit, 1 1 1 to 8 9 10 bits of the alternate function register low. So here GPIO A AFR, this low and high is corresponding or is configured as a buffer in this schemsys file. So AFR of 0 means low, AFR of 1 means high. That's it. So here I just want to set 8 9 10. Again AFR of 0 11. I'm just going to clear this for setting the alternate function 7 for configuring the PA2 as USART TX pin. And next thing is we just want to set the baud rate for the communication. So that can be set by using this particular line. You can see this is the expression for calculating the baud rate. This peripheral clock is nothing but 16 megahertz, and this baud rate is nothing but the baud rate that we are passing as a parameter to this function, and again the baud rate right over here. So this is the formula for calculating the baud rate. Whatever the baud rate that you are providing right over here will be set, and this BRR is the register for setting the baud rate. And let's move to the control register of USART for setting the transfer direction and also for enabling the UART module. And in this USART CR1 control register, you can clearly see the bit number T3 is useful for enabling the TX operation, and the bit number 13 is useful for enabling the UART module itself. You can see bit number 13 is UART enable or USART enable, and bit number 3 is transmitter enable. So here I am just going to set CR1 bit number 3, and here I am setting bit number 13. So that's all about the USART init. Here I can just now call this function in my main with the baud rate mentioned right over here. Let's take it to be 115200, which is the standard baud rate. And similar to LED, I just want to include the USART header in my main program. And this USART write function, as I mentioned, it will be helpful for transferring a byte of data to the UART bus. So whatever the data that I am passing right over here, a byte of data will be transferred to the UART bus. So here I will just check for the USART2 status register bit number 7. If it is not high, I will wait here. If it is high, I will just write directly to the USART data register. So USART data register, I am just going to mask and write the 8 bits. So this is the data register which we will be using for transferring the data. And in the status registers, you can see the bit number 7, that is TXE. So this bit number 7 is nothing but transmit data register empty. So what we are actually doing here is we are just checking for the transmit buffer to be empty. If it is empty, this bit number 7 will be made high by the processor, and if it is high, we are just loading the data register for the next data to be transmitted in the UART bus. That's it. And in the next UART transfer function, I am just going to loop through the same UART write function using a while loop like this. So the process is very simple. Here I am declaring a variable, local variable, and this buffer is nothing but the buffer that we are receiving right over here. And if it is having null character, if it is not having the null character, always remember string will be followed by a null character. So that is what I am checking right over here. The last element, it should not be the last element. That is what the check I have made right over here in the while loop condition. If it is not a null character, I will just write that data byte using UART write. I am incrementing the variable. I will loop through the same buffer until I reach the end. So the end means it is a null character. That's it. Now I am just going to the main function, and here I am commenting this, and here I am just going to pass sm training academy \n. That's it. So for every these two rough loop delays, I will get this printed in the UART bus. I am compiling this. Zero errors and one warning. What could be the warning? That is okay. That is it is mentioning as a char. Okay, that is okay. Now for demonstrating the UART, I am just going to use this Doclight application. Just double click on this. You can use whatever software you want for serial UART. That is purely based on your opinion and choice. Here I am selecting the STM microelectronics virtual link. The baud rate is 115200. Click on OK. Now I am not going to turn it on. Before that, I am just going to dump the flash to my microcontroller. So here I am just going to click on this particular icon for dumping the flash. It is done. Now I am just going to run this. You can see the SM Training Academy is being printed on my Doclight software continuously after a certain delay, and it is going on happening because I have written the statement inside the infinite loop. Until I stop, it will continue to print. So we successfully wrote the base level drivers for transmitting data over UART port or UART peripheral of the microcontroller STM32f4 from scratch in this particular video. I hope you learned something new in this video. See you in the next video. Thanks for watching.